Hello, AP Calculus students, Mr. Ford here with a homework tutorial. This is the first homework assignment from Chapter 7, 7.1.1. We're going to be doing select problems here. I'll guide you through which ones you need to do in order to complete this assignment. For 7.6, we're just going to do A and C, and then these questions here, E, F, G, and H, are all going to refer back to Part A. So we'll mostly be doing Part A there. We're going to do 7.7, 7.8, 7.9, 7.10. We're going to skip 11, and we're going to do number 12. So let's get into it. 7.6 is just going to test our derivative skills. We're asked to differentiate each equation with respect to x and leave your answer in terms of only y and x. So let's get into it. Question A gives us the function y equals 7 times the natural log of x plus 1 minus x squared. We are just going to take the derivative of this with respect to x. I'm just going to go ahead and write down c in this space anyway before we get started. Y is e to the tangent of x. Cool. So we just got to remember all of our derivative rules going forward here. The first thing we're going to do is we're going to deal with, well, I guess over here in question A, when we go and do dy dx, the constant of 7 doesn't do anything, but the derivative of the natural log is 1 over x plus 1, like that. Now, technically, there is a chain rule here because there is an inside function of x plus 1, but the derivative of that is just 1. So in order to help illustrate the chain rule, I'm just going to write times 1 there, just to help remind you that there is a derivative that you have to multiply by. But in this case, the derivative is just 1, so we don't really need to worry about it. And then in the next term, we have minus 2x, like that. So if you want to clean that up, the derivative is going to be 7 over x plus 1 minus 2x. That's the first derivative, y prime or dy dx. For question C, a little simpler here. This is also going to require the chain rule. The derivative of e to the x is just e to the x. So dy dx is equal to e to the tangent x power. The only problem there is that we have an inside function of tangent of x. So we're going to need to use the chain rule to multiply by that derivative. And the derivative of tangent is secant squared of x, like that. So we are going to have the secant squared of x times e to the tangent of x power, and that is your dy dx for part C. Pretty straightforward, not a whole lot of problems there. I've got my published answers here up so I can make sure we're getting the correct answers. Looks good. So, question E, we're skipping D. What is the second derivative? That's what this means here. Don't worry about the fancy terminology. That is just the second derivative. We write that as d squared y over dx squared. For the function in part A, write your answer in terms of x only. So we're going to take, for part E here, we're going to go to the next level down with this one here. We're going to look for the dy squared of, d squared y of dx squared. That's right. Here. So for this, we have two terms. We have the 7 over x plus 1, and we have the minus 2x. So we're going to deal with them separately as we think about this problem there. The 7 over x plus 1, that's going to require, well, it doesn't really require that we could use the quotient rule, but I think it might be better, maybe before we get started here, let me write this in orange. It might be better to think about this as 7 times x plus 1 to the negative first power. That would certainly help us do the derivative a lot easier. Let's just do that because we can just use the power rule there. If you want to go through the quotient rule, you can, but you will land at the same answer. But it might look a little different, and it's going to take a lot of time to get there. So this is a much faster solution. So if we're going to use the power rule with this, our negative 1 comes down and multiplies and makes negative 7 times x plus 1 to the negative second power. We're going to drop it down 1 degree. Of course, just like before, just like right here, we still have to multiply by 1 because that is a chain rule problem, and you do have an x plus 1 there. Fortunately, the derivative of x plus 1 is just 1, so we're going to leave it kind of exactly how it is. I'm going to write down to times 1 to help illustrate that chain rule here. The derivative of minus 2x is just minus 2, so that's going to be easy. So cleaning this up, looks like our second derivative, d squared y over dx squared, is equal to negative 7 over x plus 1 to the second power. minus 2. Looks like that. I'm sure we could do some algebra to combine those two terms together into one fraction, but who cares? I'm over it. Let's look at what question F is going to ask us to do. In fact, if you look ahead at these questions, yeah, what the second question is going to do is have us plug x equals 3 into our second derivative. And then later on, we're going to need that to, or well, in part G, we're going to write the equation for a tangent line at x equals 3. So we're going to go back to the first derivative. But let's do F right now. We can do that. It's no real problem. For question F, which I'm going to write here in red, all we're doing is taking our d squared y over dx squared, and we are evaluating that for x equals 3. So what that means is we're going to plug a 3 in for that 1x. It's negative 7 over 3 plus 1 squared minus 2. That's going to give you negative 7 over 16 minus 2. And you know, I guess you could stop. I don't know. Do I want to use a calculator for this? I'm going to practice not using a calculator. So 2 is equal to 32 over 16. And so that's going to be negative 39 over 16, which is the published answer also. Looks pretty good. There's part F. Let me maybe section these off to help kind of see what's going on there. Let's look at part G, which is going to ask us to write the equation of a tangent line at x equals 3 for the function in part A. So let's, I'm going to zoom out a little bit and get a good amount of space. This is a problem that we should keep practicing. This is for question F. Our original function was y equals 7 times the natural log of x plus 1 minus x squared. And we are asked to write a tangent line at x equals 3. So, to think about this problem, whenever you're asked to write a tangent line, you want to think about point-slope form from Algebra 1. Y minus y1 equals m times x minus x1. It's a formula that we typically teach back in those days, and it gets a big glow up here in in AP Calculus. We currently know that 3 is going to get plugged in for x1. That's the point they're giving us, or at least the x-coordinate of that point. So what we're going to need is we're going to need the y-coordinate at that point too. So we're going to take 3, and we're going to plug it in. We're going to evaluate y when x is 3, essentially. That's going to be 7 times the natural log of 3 plus 1 minus 3 squared. And I suspect this will not be a nice number because the natural log of 4 is not going to be a whole number. So I'm going to use a calculator to evaluate this decimal. And honestly, you could do this problem without making a decimal out of it. You could leave it in its exact form, but I'm going to use the decimal. So this is 7 times the natural log of 4 minus 9 is what I'm writing down. And it's going to be that number right there. Now, I'm looking at the published answer, though, and I noticed that the book did not use a decimal. So I'm not going to use a decimal either. I'm going to leave it as this nice general form. 7 natural log of 4 minus 9. That is what y is. We're going to call that y1 in our problem right there. And that's going to go in right for the green spot up atop. It's not going to look super nice. I mean, we can plug in right now. It's going to be y minus, in parentheses, 7 natural log of 4 minus 9, close parentheses, equals. I'm going to leave a blank for the slope, x minus 3. It's not nice looking, but that's what it is, and that's what matters. As far as the slope, which is the missing part, that's where we need to evaluate dy dx. We need to find the slope at x equals 3, and that's the derivative. And fortunately, we have the derivative formula right over here. It's 7 over x plus 1 minus 2x. So that is going to be 7 over 3 plus 1 minus 2 times 3. And double check, make sure I got that right. Yeah. And that'll be a little nicer than its original counterpart. This is just going to be 7 over 4 minus 6, which I'm going to think about as 7 over 4 minus 24 over 4, which is another way to think about 6. And that is going to be negative 17 over 4. And that is our slope, which we're going to plug in. I'll use a blue highlighter for that. We're going to plug that into the m right up top. And that will kind of fill out our answer, negative 17 over 4. Again, this is the answer. That is not a nice-looking answer, but that is what it is, and that's what matters. Let's look at question G. One more thing to look about. If the tangent line is used to approximate the function at 3.01, Will it give an underestimate or an overestimate, and use your answer from part F to determine your answer. So part F is the second derivative, and the second derivative is all about concavity. This is a review problem, but if the second derivative, let's say f double prime of x, if it's less than 0, we're talking about it's concave down. And if the second derivative is greater than 0, we're talking about a curve that is concave up. So let's take a look at what's going on at 3.01 in our second derivative. This is for part G. I'm going to make a little space right here. So let's talk about what our second derivative is, specifically when x is equal to 3.01. The nice thing here is that we don't really care about what the answer actually is. All we need to know if it's positive or negative. And that's an easy question to answer. You're going to have negative 7 divided by, 4.01 squared minus 2. Well, I might actually need a calculator for this because I'm not entirely sure. I believe, it's going to be negative for sure. Because this fraction here, that's going to be negative. Because you'll have a negative 7 divided by a positive number. That'll be negative. And then you're going to subtract 2 from it. So this is going to be negative. And so therefore, this curve is concave down. Now, if we think about a concave down curve like this, really anywhere, and you think about a linear approximation on that curve anywhere, maybe just draw a little picture like this, which is what I always have to do for these things. No matter where you are, these curves are always going to be overestimations because the line is always going to be above the curve. It's going to touch the curve and then go on. It's always going to be above it. So the answer here, because it's concave down, this is going to be an overestimate. Let's look at 7.7, which is going to ask us to integrate a bunch of functions here too. So we're leaning pretty heavily, as we have been lately, we're leaning pretty heavily on a lot of derivative and integral mechanics going forward here. These are going to set up for a thing we're going to do later on in Chapter 7 called U substitution, which is actually pretty simple. But what we're going to think about it right now is we're going to think about these as laying a trap, because that's exactly what we need to do. Let's talk about that with 7.7. Let's start with A. I'm going to get some room here to work with. I'm going to do, this is my work for 7.7, part A. We're talking about the integral of e to the 3x dx. We need to evaluate this integral here. So what we need is an antiderivative. We need something whose derivative is e to the 3x. That's the trick. So that's what you got to think about. You're thinking about what function has a derivative of e to the 3x. Well, an easy answer is e to the 3x because, if you take the derivative of e to the 3x, it is e to the 3x. However, if you take the derivative of this, let's just think about the derivative, d dx of e to the 3x. This is equal to e to the 3x, but you have to multiply by 3 because of the chain rule. So what we need to do is lay a trap to get that 3 to cancel out. So what we're going to say is that the antiderivative here is 1/3 e to the 3x plus c. Because what's going to happen here is when you take the derivative of 1/3, when you take the derivative of 1/3 e to the 3x, you get, at least for the e to the 3x part, you get this right here. And then what's going to happen is the 3 and the 1/3 get to cancel out, and that's what leaves you with just e to the 3x. So we're laying that trap. That's what the 1/3 is all about in this problem. Question B is going to be the integral. I got to look at it again real quick. Question B is the integral of sine of 3x. It's going to be a very, very, very similar answer too. Integral of the sine of 3x dx. Very similar solution here. If you think about the derivative of the sine of 3x, well, actually in this case we need a function whose derivative is sine, so we'll think about negative cosine, because the derivative of negative cosine is positive sine. So the derivative of negative cosine, here's how we're going to think about this problem. We're drawing a little thought bubble down here. The derivative of negative cosine is the sine of 3x, but you have to multiply it by 3 because of the chain rule. So just like before, we need to lay a trap. We need to lay a 1/3 in front of this thing for the 3 to fall into so that it's just sine of 3x when we're done. So once again, the answer is going to be negative 1/3 cosine of 3x, and don't forget your plus c. We're thinking backwards about integrals here. We're thinking about what function has a derivative of sine of 3x. We have a more formal process for this later. These answers are pretty easy, but we'll formalize that process when we look at U substitution after spring break. Question C, one more of these to look at. Question C is looking for the integral of, oh, golly willikers, how am I going to remember this? Here's what I can do. Let me get the actual problem here in front of me. Cool. For question C, we are looking at the integral of, we have a big old square bracket, 3x plus 1 to the third power plus 3x plus 3 dx. So we're going to need to think, again, backwards about all these things. We need to think of things that have a derivative of these things. So let's start with 3x plus 1 to the third. We need this to be all to the fourth power. We at least need that. Because if I take the derivative of this, what's going to happen is the 4 comes down and multiplies in front. Then I have my 3x plus 1. Then I have my third power right there. We need this chunk. That's what we need because it's right there in our derivative. So we need that, but we need the 4 to go away. We also are going to need a times 3 in front here because of the chain rule, because the derivative of 3x plus 1 is 3. So this derivative is actually 12 times 3x plus 1 to the third power. And again, we need this and not the 12. So we need a trap for the 12 to fall into. This is why in our antiderivative, we're going to have a 1/12 times 3x plus 1 to the fourth power. That way, when we take the derivative, the 4 will come down, and it will cancel out with the 12 to become 1/3. And then when the 3 comes out from the chain rule, that will divide by 3 and become 1, and we'll be left with just the 3x plus 1 to the third power. So we're thinking about how we want that 12 to cancel out, setting a trap. The other parts are not so tough. We've dealt with these other ones before. We need 3x squared over 2. It's the same thinking. We just need the 2 to come down and fall into that trap and leave the 3x behind. And we also need a plus 3x there. Now we have a function whose derivative is exactly what's going on. If you take the derivative of this, you'll get right back into here perfectly. All of the extra numbers will fall into traps. Don't forget a plus c, though. So there is your answer for this one. Let's take a look at 7(8) really quick. For each function below, we're going to calculate the average value over the given interval and state the value of t for which such g of t is that average value. We're going to do a lot of this on the calculator. We might do A by hand, but B we'll definitely use the calculator for because I don't have a way of doing it by hand. So for A, this is for 7(8), part A, we've got g of t equals 3t plus 6. And we're looking for the average value of that over 0 to 8. So, average value is a really simple formula. It's 1 over 8 minus 0 times the integral from 0 to 8 of 3t plus 6 dt. So basically you take your boundaries, 8 is there, and 0 is there and there. What we're doing is taking the whole integral from 0 to 8 and basically taking its average by dividing by 1/8, essentially. Kind of like adding everything up and dividing by however many things there are. It's the same kind of idea, just more of a calculus notation thing. We can do most of this by hand because this is not a tough one to do. Let's leave 1/8 out in front. We'll have 3t squared over 2 plus 6t. That's the antiderivative. And we're going to evaluate that antiderivative from 8 to 0. And that's a really nice one because plugging in 0 will just give us 0. So all we really need to do is plug in 8. So we have 1/8 times 3 times 8 squared over 2 plus 6 times 8. And I will just put a minus 0 on there because we are evaluating that. If we go through the trouble of doing this, we have 1/8 times, let's see, we have 3 times 64 over 2. And I'm going to think about that as 3 times 32 because 64 over 2 will become 32. And then 6 times 8 is 48. So we have 1/8 times, I'm crunching numbers in my head, 96 plus 48. And this is my weakest math point, I'll be honest here, is doing math in my head. 96 plus 48 is 104 plus 40, it's 144. And I do not know if 144 divides by 8 evenly. I'm just going to check it really quick. And it does, it's 18. Hey, cool. Hey, groovy. The second part of this problem is, okay, we get the mean value theorem says that there has to be some place along the graph where this function actually equals 18. So we have to solve this problem. Hey, 3t plus 6, when is it actually equal to 18? Fortunately for us, that's a pretty easy problem to answer. It happens when t is equal to 4. There you go. For the second part of this question, we are going to use the calculator. I'm probably going to end up using Desmos too, just to show you visually what's going on. Here our function is 3 times e to the t power, and we're on the interval from 0 to 1, which makes this process actually really simple. I'm still going to use the calculator for it. So the average value is equal to 1 over 1 minus 0 times the integral from 0 to 1 of 3 times e to the t power dt. Again, I probably don't need a calculator for this because I can probably do it by hand, but, you know, I'm going to use it anyway because we probably want a decimal answer anyway. Probably, I mean, if I try to do this by hand, I'm going to end up with an answer that's in the term of e to some power. So, you know, actually, on second thought, I am going to do it by hand and then check the math on the calculator. That'll be easy. So this will be 1 over 1 in front, which makes this problem much easier. And it's the integral from 0 to 1. I'm actually going to do the antiderivative right now. The antiderivative, that's just 3 times e to the t, honestly. You can leave the constant number of 3 alone. And we're going to plug in 1, plug in 0, and call it a day. So this is actually really simple. It's just going to be 3 times e minus 1. Because e to the 0 power, if I show my work, 3 times e to the first power minus 3 times e to the 0 power, which is going to be 3e minus 3. Whoops. See, I'm glad I showed my work. Or you could factor out the 3, I suppose, if you wanted to. This is the average value. Now, what we're looking for, let's see. We're looking for a time when the original function equals that. We're looking for when does 3 times e to the t equal 3e minus 3? There's probably a really easy way to answer this question. Without a calculator? Oh, you know what we should do? Whenever you have a problem like this that involves a variable up in the exponent, you should just take the natural log of both sides. What that will do is it'll pop the t down as a multiplier in front. Natural log of 3e minus 3. And so t is going to equal the natural log of 3e minus 3 over the natural log of 3e. You can get a decimal for this. Also, you know, I don't know. We could talk about all the logarithm rules that work here too. I mean, I'm good with this answer. I want to be done with it, but you can shake this out a little bit. This is also equal to natural log of e minus 1 because you can cancel out a lot of it. Natural log of e is just 1, and there's ways you can rewrite these logarithms, but I'm kind of over this problem right now, so I want to move on to the next one. I only like the first part of the answer anyway. Let's look at 7-9. Sand is being poured into a sandbox, and it's got a conical pile with a radius of r and a volume of v, and all we got to do here is interpret what dv dt and dr dt mean. And these are really easy questions. dv dt is the change in volume over time, and dr dt is the change in radius over time. And that's it. Honestly, that's all there is to it. dv dt, dr dt. Change in volume, change in radius over time. Prepping for more of our fun adventures with related rates. 7-10, we're going to sketch the region bounded by y equals x to the fourth and y equals 1 and calculate the exact value of the region. I'm going to need some space over here, I suppose. You know, I'm going to keep working down. No, I'm going to go way off to the side here. 7-10, 7-10, 7-10. So our functions are y equals, let's see, x to the fourth power and y equals 1. I'm just going to double check that really quick before I get too far into this. Yes. Perfect. So the first thing we need to do is make a sketch of this really quick and just kind of think about how these functions behave. X to the fourth is pretty much the same thing as x squared. It's just a little steeper. And y equals 1 is just a straight horizontal line. So I'm just going to go ahead and draw y equals 1 first, like that. And I know that x to the fourth power has points at 1, 1 and negative 1, 1. So the region is just going to look kind of like this. It's just like it's like a parabola, but it's a little more steep. A little bit more of a flat bowl at the bottom than as a round bowl. It's going to kind of look like that. You can confirm that on a calculator if you want to. It's up to you. In fact, I might do that right now in the bottom right corner of this screen because I can. X to the fourth and 1. And our window is just going to go from -2 to 2 for x, and we'll go from -1 to 2 for y, and we'll see that region developing. There's your parabola, and there is the straight line. As far as finding the volume of this, since the blue graph is always on top of the red graph, we should use an integral. And we're going to do an integral from -1 to 1 of the blue graph, which is y equals 1, minus the red graph, which is x to the fourth. dx. That's all we're going to need to do. It's actually going to work out to be something pretty nice, I suspect. So now it's just a matter of evaluating this integral. Taking the antiderivative, according to the fundamental theorem of calculus, we have x minus x to the fifth over 5. That would be the antiderivative of this. If you took the derivative of x, you get 1. And if you took the derivative of x to the fifth over 5, the 5 would come down, fall into the 1 over 5 trap, and x would come down to the fourth power, which is what we want. We don't need to put a plus c on this because we are evaluating this from 1 to -1. So we're just going to do the operation of plugging in 1, plugging in -1, and subtracting. 1 minus 1/5 minus -1 minus -1/5. And this is a pretty easy operation to do without using a calculator because if you realize what's happening here, we're just going to be adding these things to themselves. So we're just doubling it, honestly. It's going to be 2. Oh, maybe not. Minus 1/5 minus 9/1. It's going to be 2. Is it 2? Is the answer 2? Would the 1/5 cancel out? Am I thinking about that right? Am I thinking about that correctly? Do the 1/5 just cancel out? -1/5 minus -1/5. That would be a 0. So it's going to be 2. I think that's the answer. I'm just going to confirm that really quick. Nope, I'm wrong. What am I thinking about incorrectly here? Oh, you know, I guess if I'm thinking about this correctly, that minus -1/5 can become a plus. So let me actually shake up my thoughts on this one. See, I'm not thinking about this algebraically enough. This is going to become a plus 1 when you do minus -1. I'm thinking about this right here. This minus -1/5, that's a plus 1/5. So this is actually a minus another 1/5. So what we have here is you have 1 plus 1 is 2. We have minus 2/5. And if I think about this, that's 10/5 minus 2/5, which is 8/5, or 1.6. If I'm thinking about this in, that'd be units squared if I really wanted to put a unit on there. 1.6 units squared. There we go. That kind of fits. If I look at the graph really quick, if I bring that calculator cam to the front session so I can look at it. I warm the, hey, hello. Oh no. There you are. That kind of fits. 1.6? Sure. 2 would be this rectangle if I just draw a straight line down here and across like this. So 1.6 kind of fits in that little area right there. That makes sense to me. Okay, and the last question we got to look at, and then we're coming on 30 minutes here, which is quite kind of long for one of these, but it's the only one you have over the spring break. So 712, assume the altitude of a flying kite remains constant. So right away, I'm going to kind of think about that sentence right away. On this picture, the altitude is constant, so there is going to be no change on the vertical end of this thing. That's not changing. As the length of the rope K changes, the kite flies horizontally, either toward the person or away from the person. So if T represents time, are dk dt and dx dt positive or negative? Interesting. Well, let's see. Well, it's going to depend on if the string is being let out or brought back in, because that's what K is. K is the length of the string. Let's see, toward or away from the person. Let's see. I think dk dt. dk dt is the length of the string, the change in the string over time. Whether or not that's positive or negative is going to depend on Whether you're letting the string in or out, I think. If the kite flies horizontally, either toward the person holding a rope or away from the person. Well, see, this is I have a problem here because I disagree with the book's answer. The book says that both are positive no matter what. dkdt and dxdt are both positive. And I'm thinking, well, you said in the problem yourself that the kite could fly horizontally either toward or away. And I think it would depend. In my mind, if the kite is flying toward me, I'm pulling the string in, so dkdt is negative because it's changing. So if the kite is flying toward me, dkdt and also dxdt will be negative. But if the kite is flying away from me, I'm letting out more string. So that means that dkdt, the rate at which the string length changes, and therefore the horizontal length changes, is going to be positive. And that's because the height is not going to change. The altitude is constant right there. As far as the way dx dt changes, I mean, you can think about this. I think right now we're not really focusing on formulas at all. But keep in mind that is a constant height right there. What I want you to see is kind of this Pythagorean Theorem thing happening here, where their relationship here is that a squared plus x squared equals k squared. That's kind of the relationship that we're going to build off of right there. If you think about this as you let more string out, or as you think about, like, pulling the thing back in, it depends if you're pulling in or pulling it out. But the way x changes, dx dt, if you think about the rate at which that's going to change, it's going to, well, let's think about it starting off right above you, where let's say that dx dt is 0. It's going to increase very, very quickly at first, but then as you let more string out, as x and k approach being the same number, they're going to start approaching each other the same rate there. So it's going to increase quickly. And then it's going to approach whatever dk dt is. It might be more helpful to think about this just as a right triangle. Like, just think about this. Like, you have a right triangle where this is not, that side is not changing, and the only thing that is changing is the diagonal. Let's say dc dt, like that. Think about how b is going to change. That's really what we're thinking about. How is b going to change as c starts increasing? I mean, at first, as c increases, b goes very, very quickly. I mean, the difference between these three different blue situations, you can see that b is increasing very fast. But as you get a really long triangle right there, you start to get this idea that the hot top of that triangle is not going as fast as it used to on its first way out, but then it's going to start to match what the rate of change is for the diagonal over time. So over time, dx dt and dk dt will be about the same thing, but we'll be able to explore that in more like quantitative, formulaic reasons later on. Right now, all I need you to understand is that there is such a thing as dx dt and dk dt, and we could think about them there. So we'll leave that as it is. I hope you guys are having a great spring break when you watch this video, and I hope this is starting to really click. I think we've hit our stride as a class. A lot of us have, and just keep going, man. You're almost there. You're almost to the finish. We don't have a super amount left, honestly. We're only going to do one section in Chapter 8. We only need to, as it turns out. So we're pretty close to the end here. We have Chapter 7 with related rates to look at, and then related rates, use substitution, and differential equations, and then a handful of things in Chapter 8 with three-dimensional revolutions. That all sounds like a lot, but it's actually only about a month's worth of work, which is about perfect. So you guys have done a great job this year, and you should keep it up. So I'll see you in the next video, and have a great spring break.